Good evening. It is 7 p.m., but nobody has yet joined. So we will wait for some more time before we start. Thank you. Good evening, everyone, and welcome to week 10 of the live sessions for Fundamentals of Additive Manufacturing Technologies. I'm Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. I work in the broad area of additive manufacturing, and let's get started. So, we'll start with a short recapitulation of the contents that were covered this week, and then we'll solve some illustrative examples that will help you in solving your assignments. So, this week resumed with the powder feed additive manufacturing technologies and started by looking at the discrete coaxial nozzles and their dynamics. So when we're talking about discrete nozzles, of course, there would be multiple and usually are three to four. And by delivering three to four simultaneous jets of powder focused around the same point, several new considerations are introduced, such as the inclinations of these channels with respect to each other, which would actually shift the location of the powder stream's focal point. Also, because the powder streams come and collide at the same point, their velocity is affected as well as their final distribution and the spatter. Also, if we keep the total inlet gas flow pressure constant, then that gas pressure would be divided or the flow rate would be divided among all the coaxial nozzles. Thus, the flow characteristics will also change. Again, the number of powder streams has a significant influence on stream characteristics and on the catchment efficiency. We'll also look at a simple calculation for the catchment efficiency in the upcoming slides. And studies have demonstrated that with increase in the number of powder channels, the particle velocity in each of the delivery streams reduces. And because of this reduction, the bouncing off effect is reduced. So not too many particles impact the melt pool and bounce away. In fact, they will be collected in the melt pool itself and will contribute to the mass flow rate. And thus the clad area increases. Thus the catchment efficiency increases as well for the same set of process parameters. And here we have some qualitative relationship between some of the nozzle design parameters and the powder flow rate. So the powder mass concentration is negatively correlated to the nozzle exit diameter dn. So larger the diameter of the delivery nozzle, of course, we can guess for the same amount of powder, it will be distributed over a larger area or a larger volume, and thus the density would be lower, as well as the injection radius. The standoff distance, which is basically the distance between the nozzle exit and the focal point or the area or the region, the plane where the area of the powder stream is the least, has a negative correlation with injection angle and nozzle exit diameter. A negative correlation means inverse proportionality, so it can be represented as and SD is inversely proportional to dn. Thus, an increase in either of these quantities decreases the standoff distance and moves the focal plane closer to the nozzle exit plane. In the previous session, we looked at how the standoff distance has to be optimized. If it is too low, then the nozzle can be damaged as well as the laser optics can be damaged. And if it is too far away, then my working area would be out of the focal distance. Thus, I will be only working with a deep focus beam of laser or a deep focus stream of powders. Again, the injection radius is positively related to the standoff distance, and increasing the injection radius would increase the standoff distance. So these are just some of the qualitative relationships which you can appreciate by looking at just the diagram. And some of the design considerations when we are using these discrete coaxial nozzles is the omnidirectionality. And in brief, omnidirectionality means that irrespective of the direction in which my laser deposition head is moving, I should achieve the same powder deposition characteristics as well as the same mechanical and metallurgical properties. Let us see how this will be affected when we are using multiple discrete powder nozzles. So first of all, the area of the overlapping powder streams should be more than the laser spot size so that the uniform deposited track is uniform. Of course, this will decrease the catchment efficiency. But if our laser spot die itself is larger than the powder stream, the melt pool will be far larger than the area in which I am actually depositing the powder, which would lead to creation of an unnecessary heat affected zone. And again, it is necessary to ensure the uniformity. And the correct standoff distance should also be used, as we already discussed. And if we look at the diagram to the left here, I will just enlarge it. So we have four streams of powder which are converging at a point. We see that in these areas, which so this has also been illustrated by Professor Kapil, I'm just repeating it. Say these regions 1 are areas where the powders from only one powder stream are present. Regions 2 are the regions where there's an intersection between powders from two streams. Similarly, there are these regions, other regions, and more importantly, this one right here in the center, where I am getting an intersection from all the powder streams. Thus, it is this region only which will have the maximum amount of density of area density of powders. And in the neighboring regions, as we can see, because of the change in the density, say here, the density is different in the green region. Again, in the region highlighted in black, the density is different again. So within the laser spot radius, I have three different densities of the powder. Thus, the deposition characteristics will be different, and it can be expected that the end mechanical and metallurgical properties will also be different. Thus, this case is not omnidirectional, and the properties that I obtain will be subjective based on the direction of deposition. To ensure directionality, maybe we can align our powder streams in such a way that in the entire region which is under or interacting with the laser spot size, my area density of powder is constant. As well as we see that even in this greater region surrounding the laser spot size, which is not really interacting with it, the powder density is same as within the bounds of the radius of the laser. So of course they're compromising on the catchment efficiency, but this is important to actually ensure omnidirectionality of properties. So even if some of the powder is wasted, our end product will have favorable properties, and that is what the end goal of this process is. So FGM fabrication comes later. We'll look at it. Again, another consideration which has to be taken into account is the nozzle tilt. And logically, if you think about it, when from a continuous coaxial nozzle, so it will maybe have a donut-like cross section, and or from a central feed nozzle, if the powder is flowing, because of the effect of gravity, the gravity will act on particles which are coming from the top edge, and they will be influenced to move in the towards the bottom. Thus, we see that there is a greater density of powders towards the bottom region compared to the top. So, in this region, we will have a lower density of powders. Again, this may lead to a lack of omnidirectionality, and my powder deposition characteristics will not be the same. Say I am depositing a bead on a surface, maybe one side of it will have higher density of powders, whereas the other side will have lower density because of this nozzle tilt. How can this be corrected by the use of continuous coaxial nozzles or discrete coaxial nozzles? So we know that we can regulate the gas flow rate through each of these nozzles independently. So if I can have a higher gas flow rate, say I put it as say, V3 and V2 and V1, if these are the gas flow rates through each of these, if I can ensure that V3 is suitably larger than V2 and suitably larger than V1, then I can ensure that the final powder profile coming out of being ejected from the nozzle is uniform. And thus I can maintain my omnidirectionality. Thus, by simply increasing the drag velocity of the carrier gas, this problem can be solved. Again, if the laser is fed centrally, what happens is, this is my laser profile here, and we know that the power distribution or the intensity distribution would be Gaussian, so something like this. And we can see that its effect is seen in terms of the meltful dimensions. And meltful, wherever the power is the highest, the meltful is the deepest. And where the power is the lowest, we see that the meltful is also at the least depth. And for a powder stream which is coming from the sides, we can see that any powder particle, such as X marked here, has a far longer time of interaction with the laser. So it is interacting over this entire distance compared to any other particle, say X1, which is coming from the bottom. So it has only a very short time over which it interacts with the laser. Thus, because of this shorter interaction period, it might not even absorb enough energy from the laser, or might not even melt and remain in a partially melted or unmelted state compared to any other particle which is coming from the top. Thus, this might result in insufficient heating at the edge of the melt pool and excessive heating at the center. Again, at the edge of the melt pool, we might have a greater number of unmelted or partially melted particles, whereas the particles at the center or towards the center would be fully melted. The tracks so generated might show a lack of fusion with the substrate at the edges and excessive dilution at the center. We know that some degree of dilution is necessary to ensure that there is metallurgical bonding between successively deposited layers or between the layer and the substrate. But if this dilution is excessive, then my melt pool might permeate into several pre-built layers. Also, in cases where I'm dealing with, say, an overhanging feature or a very thin feature, this melt pool might simply melt through that entire feature itself, destroying it. However, one advantage of using a central feed powder driven nozzle is the minimal divergence of the powder stream, since all of is being delivered coaxially. And for coaxial nozzles, however, the efficiency can be very low, such as low as 30%. Whereas for central feed nozzles, the efficiency is above 80%, which is of course far, far better. Here we have data from a paper which shows the bead profile depending on the energy profile which is being used or the energy distribution. So in the first case, we have a sort of distribution which shows very low dilution and very low depth of penetration into the substrate. Then we have two top hat types energy distribution, and finally the Gaussian distribution, which shows the maximum amount of dilution and maximum amount of penetration into the substrate. Thus, for modeling purposes, usually we use Gaussian intensity. However, we may also have other intensity distributions, and depending on the application, they may be suitably used. Again, for most of the commercially used or commonly available powder-based additive manufacturing machines, we use these pneumatic nozzles, which use a pressurized carrier gas to actually deliver the powder. The carrier gas also serves many other purposes, as we looked at last week, such as protecting the laser optics from the generated fumes and particles, and delivering the powder feedstock, of course, as well as shielding the molten pool from atmospheric oxygen. However, a second class of nozzles, such as non-pneumatic nozzles, also exist, or at least they have been theorized. They are not very commonly encountered or used in any commercial machines as such, but the concept may catch on in the near future. So, because of the use of the carrier gases, the very high particle velocity leads to a decrease in the powder catchment efficiency, as well as the deteriorated surface finish, because the high velocity particle might impact the melt pool and then simply bounce off. Again, because of this high velocity gases, uh, they interact with the free surface of the molten pool and may lead to turbulence or disturbing the free surface, which can lead to poor surface finish. The use of conveyance and shielding gases also increases the convective cooling of the melt pool and thus creates high energy loss and dispersion. And the powder particles with high velocities, upon impacting the free surface, often generate a force of sufficiently high magnitude And such tracks can show very high dilution at the center and lack of fusion at the edges, as we just discussed. Again, this carrier gas can also get entrapped inside the melt pool and may lead to gas-induced porosities, which is also detrimental. Here we also have a comparison of non-pneumatic and gas-assisted nozzles. We see that the cross-section, a larger cross-section area is deposited. The porosity is like one third, uh, only one third in a gas as compared to a case of gas-assisted nozzle, and the surface roughness goes down by a factor of 7. So this is really significant. Yet the non-pneumatic nozzles do not find common usage, and this mostly has to do with the complicated design as well as the unregulated or difficult to regulate mass flow rates. So we can make the powder feedstock flow, but we cannot really control it very precisely as of yet. Of course, new technology is up and coming, and such non-pneumatic nozzles may also see light of the day in the near future. Here, some of the published or proposed non-pneumatic nozzles are discussed. So often they will use this piezoelectric. So PZT actually stands for lead zirconate titanate, and these work on piezoelectric effect. So by giving a vibration, torsional vibration to this glass filled tube, that is, it will move along the directions, oscillate the powder which is filled inside it, which will nominally be blocked because of the arch formation. So as we discussed, the powders here may form an arch sort of structure and retard powder flow. These may be made to flow by giving it a certain vibration. Again, a ring type PZT can also be used as shown in the example to the right. We can also use some ultrasonic means such as using this sonotrode in a water bath. Thus, the sonotrode transfers the ultrasonic vibrations via this water or working fluid to the tube which has the powder feedstock filled, and then it can be made to flow. Similar principles can also be used for using or depositing multiple powders or depositing FGMs. Here by using an acoustic waveform generator. Again, here we have both horizontal and vertical piezoelectrics, and similar to this case here, where we have a centrally delivered laser and a continuous annular powder flow channels. In summary, the common powder flow characteristics are related to some of the process parameters, such as the high mass flow rate is often associated with increased surface roughness and track porosity. So, if you want to increase the deposition rates, simply increasing the mass flow rate may actually lead to worse surface finish and more porosity than before. Again, a lower particle velocity is preferred to increase the catchment efficiency, and the feedstock should be carefully selected because reflective materials such as aluminum and copper are often difficult to process using the conventional IR lasers. And the melt pool size for conductive materials are very small, which leads to poor fusion with the pre-deposited layer or the surface or the substrate. And thus, a smaller focal point of powder stream must be used in such cases. Or the other way is to use actually lasers of smaller wavelength, such as blue lasers, are commonly used for processing copper, and they have been successfully demonstrated. However, for metals, as we know that usually the wavelength used is some 1,000 nanometer or sorry, 1 micrometer. So while this is suitable for most metals, for highly reflective metals such as aluminum and copper, we might have to opt for shorter wavelengths. Similarly, if the shield gas is used, of course, it will prevent the melt pool oxidation and also the laser optics. However, it might also get entrapped and might induce turbulence on the free surface of the molten pool. Omnidirectionality is a concern. And so for some of the technologies, such as electron beam based additive manufacturing, where we saw how there is a need for maintaining the vacuum both in the working chamber and in the gun chamber. We need to maintain vacuum because A, the electrons are very light particles, and if they come in during their motion, if they come in contact with any other heavier molecules, they will simply lose all of their kinetic energy and bounce off. Thus, they will not reach the surface. Again, in the gun chamber, the filament is subjected to very high temperatures, and if some other molecules are present there, it might lead to oxidation of the filament and reduce its life significantly. Thus, in electron beam based systems, in the presence of vacuum, it is simply impossible to deliver the powder feedstock by gas assisted means or using a carrier gas. In such cases, these non-pneumatic nozzles may definitely be of use. Currently, powder wire feedstock is used with electron beam setups, and powder feedstock is used in powder bed type of additive manufacturing. However, it is impossible to use powder feedstock in a say a DED-like process where the powder is delivered actively using some carrier gas. And we'll look at some of the examples of the popular machine or the commission machines which use this technology. So one is Optomec, developed in Albuquerque, USA. We also have a few Optomec machines here in India. So I have a graphic which showcases where in India we have all these DED setups and some of the information related to it. I'll show it after this slide. And it can have both open and control atmospheres as well as hybrid and standalone systems. Again, we have ones developed by DMG Mori, which are mostly the hybrid type and have used a laser deposition head retrofitted in some cases to existing 5-axis CNC vertical milling center. These gives it versatility as well as the ability to produce overhanging features without the need to deposit any support structures, as well as the part can be finished in the process itself. It does not require any post-processing as such. This is another DD setup made by Beam in France and uses, depending on the model, it can go up to some, say, a 2000 watt or even up to 4000 watt by using a fiber laser and can have large build volumes. As we also know, some robotic manipulators or high degree of freedom robotic arms can be used to deposit these powder feedstock for a powder-based additive manufacturing process. And here is an example by BLM Group from Milan, Italy, who use three jet powder nozzles and a 3 kilowatt laser of wavelength 1070 nanometer, so close to 1000 nanometer or 1 micron. And mostly we see that all of these machines either use either a 5-axis or a 3-axis CNC machine. One of them also uses a robotic arm. But usually the case is that you will find a laser deposition head simply retrofitted adjacent to the existing vertical milling head of any 5-axis CNC setup. And the commonly encountered wavelength is of 1 micron. And usually the lasers are solid state lasers such as diode coupled fiber or fiber lasers. This slide presents an interesting study where the overhanging features have been realized without any support structures or by removal of the powder feedstock later. So the hollow structure is built as we see in the first picture here. And when it comes time to deposit the top surface, the entire area is filled with powder. And yeah, so first the part is built up to the point where no support structure is needed. And then once the cavity is available, it is filled with powder. So we simply deposit powder in this region by turning off the laser. So here it is only a powder deposition pass without any melting or sintering. Later, once this powder is deposited, we defocus the laser and use it to perform a sintering operation, such as we saw in electron beam additive manufacturing, or I think as we will see in the upcoming weeks. Now, what this does is it does not really melt the powder, however, it sinters it and produces some sort of support structures. And this thin sintered surface layer on top of the powder can act as support for the next layer to be deposited. Also, it provides a protective layer that prevents the powder below it from being blown away by the argon gas. Once this is done, we deposit the powder on top of this centered layer by switching on both the powder delivery as well as the laser optics. And I realize my hollow geometry, such as a hollow cube in this case. Later, by depositing some cavity or by some other means, the powder in the interior can also be extracted. And this technique has been used to make such duct-like features as illustrated here. So let us look at the image which shows the various DED facilities, laser DED facilities available in India. So this has been compiled by Mr. Jitendra Chaurasia, who is an additive manufacturing expert, and I have sourced this image from LinkedIn. So you can look at his profile for the original image, and all credit belongs to him. And here we see that we have laser DAD setups in only a select few places. Of course, the powder bed setups are more ubiquitous. For instance, in West Bengal, we have them in three locations in Durgapur, CMRI, which is indigenously developed, in IIT Kharagpur, which uses an Optomic machine of 2 kilowatt power. Again, it is a 5-axis CNC hybrid. And in CGCRI Kolkata, again, made by Optomic, however, of lower power of 500 watts only. IIT Jodhpur is another one which have developed an indigenous laser DED setup. Then we have the one at RRCAT, again indigenously developed by by Dr. CP Paul and team. It uses a laser power up to 2 kilowatt, and it has 5-axis CNC control. At IIT Bombay, we have two such machines. One is an indigenously developed using a 3 kilowatt laser head and uses a robotic manipulator with 8 degrees of freedom. So this has been developed by Professor Ramesh Singh of Machine Tools Lab. Another one is the Meltio machine, which so we have two machines supplied by Philips Machine Tools India. One is the Meltio M450, which is just the additive setup. So it has dual wire functionality and uses the wire feedstock. The other is the Haspas Meltio CNC integration, which also can work with two wires as well as with four powders. So that is a hybrid setup as it also has these machining or subtractive manufacturing capabilities. Both of these are available here at IIT Bombay, and others are available in Bangalore, in Trivandrum, as well as in IIT Suratkal. So this is a very useful infographic that I found. And now let's look at the second set of slides for this week, which discuss the powder feed AM process modeling in terms of the process parameters, the catchment efficiency, and the bead profile, and some of the important strategic applications of this technology. So as we had discussed in one of the earlier sessions, the process is controlled by a multitude of process parameters. However, we don't change all of them. Often most of them are fixed in choice by the manufacturer that we bought them from or the type of technology we are using. And even the ones that can be changed, not all of them need to be changed so actively. And we fix most of them, such as, say, the volume flow rate of the uh, inert gas, which is usually set to some, say, 10 liters per minute or so. The laser spot size, for instance, is again usually kept fixed. We may change it for some defocusing or some sintering cycle, but usually for a deposition cycle, it will not be changed. And other things, if often for a given material set and a type of deposition, even the standoff distance is optimized. So only some parameters are changed. So here most of them are listed. So in terms of the laser parameters, we have the power, the beam diameter, beam profile, which is usually Gaussian, the working distance wavelength is fixed, the type of feeding, the materials and design, or the motion or path, such as the track overlap ratio, the head spacing, the deposition path, the interlayer dwell time, or any preheating temperature if applied. We know that laser DED has actually been developed from the laser cladding principles. And here we have a simple expression derived for the catchment efficiency of a laser cladding principle with the assumption that the powder is side fed. So it is being fed from the side. We know that later the technology was changed, but this is for the very primitive or very simplest case. And essentially, we may define this catchment efficiency as the mass of the clad layer or the mass of the layer that is deposited by the mass of the powder that was ejected from the nozzle in total into 100. So for 100% efficiency, it would imply that all of the powder that was ejected by the nozzle in the same time period got deposited in terms of the clad layer or in terms of the bead. Of course, this will never be one. And to calculate it, we simply need two things: the size of the molten pool, as only the powder striking in this region of the substrate will be cladded, and the total amount of powder striking on the surface. This can be worked out in terms of the areas. So we have already seen how the area that is projected here for the cylindrical beam will actually be an ellipse because of the inclination, and the projected area would actually be pi by 4 pi dp square by 4 cos theta. The size of the melt pool can be approximated from Rosenthal's equation for a moving point source. Of course, this includes many approximations. It is highly approximated, but still it gives us some qualitative idea of the characteristics. I'm not delving much into the derivation. It has already been covered in depth by Professor Kapil. And the thing to note here, or the most useful conclusion for us, is to note that the catchment efficiency is directly proportional to square of the laser power. It is inversely proportional to square of the laser beam diameter and inversely proportional to the thermal conductive square of the thermal conductivity, as well as it is inversely proportional to the difference in the melting point in the square of the difference in melting point and the ambient temperature, and directly proportional to the angle of inclination of the powder feed. So using these proportionality relations, some of the numericals in this week's assignment can be worked out. So we will also solve a few examples in our problem solving session, which is coming up next. So for now, let us look at the stream characteristics in the working region. As we know, once the stream of powder is ejected from the nozzle, it will continue to converge until it reaches a region or a plane where the powder diameter is the least. From there, it will start to diverge again. This minimum region, which is marked by cross section, the section AB here, is actually called the focal plane or the focus. And say above this in the region 1, we are not really interested because the powder is not really interacting with the laser. It still has a donut-like or annular profile. However, it will interact in regions 2 and 3. Again, similar to the intensity of power in the laser beam, the very powder delivery characteristic also will form a or follow a Gaussian distribution. And the powder stream's spot radius at the convergence or focal plane is determined by the location at which the particle density is 1 by e square of the maximum. So this radius or this boundary that we see here is not really a sharp boundary because there will be powder particles located outside this boundary as well. However, for all intents and purposes, we concentrate our efforts only in this region, which is defined by where the particle density is 1 by e square of the maximum, because this is where most of the particles or the useful number of particles would be located. Thus, the particle number concentration at any point xy in a cross section can be determined in terms of the maximum concentration or the maximum number density, the distance of the point from the center or the axis, and this capital R, which is nothing but the radius of this, my sharp radius or the radius of the region. Again, I can calculate my primary efficiency in terms of these parameters, which are the width of the melt pool, and in terms of the variation in the the powder stream radius as a function of the Z height. Here, it is important to know that the Z is considered positive along the bottom direction. That is the convention which has been followed in this derivation. And it can be readily seen that the primary efficiency of the powder is a function of melt pool radius and the powder flow radius. We can also introduce an additional efficiency parameter called the powder utilization rate, which is denoted by eta U, because we know that the particles are impinging on the melt pool with very high kinetic energy, and not all of them will get melted or assimilated into it. Some of them will also bounce off. So this parameter takes care of those considerations. And finally, we can obtain the height of the melt pool in terms of these other parameters, or inversely, we can find the width of the melt pool if we can determine the height experimentally, say by measuring with vernier calipers. However, it is important to know that this derivation includes several simplifying approximations, such as Rosenthal's equation for a point or heat source, a point heat source. To make it more accurate, we can use say, a surface heat source or a volumetric heat source. Also, so this exercise is somewhat similar to one of the previous ones where for the MIG additive manufacturing process, we determined how the optimal value of step over or the optimal hatch spacing in the case of this parabolic bead profile is nothing but equal to the two-third times the bead width. Now, we have been mentioning dilution. So, how is it mathematically defined and what are its consequences? So, usually the dilution ratio would be defined as alpha equals delta by beta plus delta. And so, beta is basically the height of the bead above the substrate. Delta is the depth of penetration of the melt pool into the substrate. And my alpha, which actually gives the dilution ratio or the dilution parameter, is this depth of penetration by the total height of the bead into 100 to express it in terms of percentages. I have also seen work where this dilution parameter has been expressed in terms of areas. So say area of the penetrated area where the melt pool has penetrated into the substrate by the total cross-sectional area of the entire bead, and that has also been used. And we understand that some value of dilution is definitely optimal. It is necessary. If I have zero dilution, it simply means that the bead of material which I have deposited on the substrate or on the pre-deposited layer, it is not fused or bonded with the existing material. Thus, the metallurgical bonding is very poor or simply non-existent. Thus, there is no actual contact or connection between this newly deposited layer and the previous one, and it will simply fall off. Again, if this dilution is too large, multiple things can happen. Say in the case of an FGM, I want to control or very precisely control the composition of each of these layers. But because of this dilution effect, the composition of the previous layers would be changed because I'm introducing some additional material into it, which might be of a different composition. Also, because of the molten pool behavior or the flow of liquid in the molten pool, the distribution of these alloying elements and the chemical composition will also change. Again, if I have very thin features, because of this very large depth of penetration and consequently the large dilution, the feature itself might get destroyed. So some optimum range has been empirically worked out or experimentally observed and recommended. So, and this range is actually some 10 to 13%. If the dilution ratio is more than 30%, then keyhole porosity or keyhole type fusion is mode fusion is said to have occurred, and the process is said to proceed through keyhole mode, where these very deep and narrow melt pools form. Or if this dilution ratio is less than 30%, then lack of fusion is said to have occurred, and some lack of fusion pores may be expected. In the keyhole mode also, pores are expected because with the laser, some of the gas also travels into the melt pool, gets trapped and stays there, and later gas porosity is observed. So yeah, neither of these is desirable, and we need to keep the dilution in check and within 10 to 30%. A parameter which is commonly used to assess the type of effect or the type of mode of energy transfer which we may observe, whether it is the keyhole mode or conduction mode, is the global energy density parameter. There are others as well, such as the linear energy density, which is simply the laser power by the velocity of scanning or the scan velocity. Or there can be the volumetric energy density as well, which is the laser power divided by the volume flow rate. So this scan velocity into the height of the layer into the width or so on. One of the parameters which is highlighted here is the global energy density, and it is used to investigate the interlayer and intralayer porosity due to lack of fusion and keyhole. Region with a very low global energy density will likely observe a lack of fusion and will have lack of fusion induced porosities. So these lack of fusion porosities are actually say irregular and elongated, whereas a keyhole porosity would usually be perfectly spherical and small. The region with very high global energy density will be subjected to some of these keyhole porosities. The other defects for these powder feed based additive manufacturing methods are similar to ones discussed for the tungsten inert gas welding, the metal inert gas VAM, and others, such as the residual stresses, which cannot totally be eliminated but can be relieved to a certain extent by using techniques such as, say, laser shot peening or ball peening. The porosity, which may be because of the entrapment of the carrier gases or because of the gas pickup by the feedstock itself. So the powder feedstock or the wire feedstock may also pick up some gas, and we know that the solubility of gases in metals is different in the molten and in the solid state. So while the metal is getting melted into the melt pool, it can dissolve certain gases. However, later when it is solidified, the solubility of gas decreases and that gas is released, leading to porosity. And also, as we just saw, there can be some lack of fusion porosities as well. And crack and delamination can refer from these residual stresses and other factors. Now, let us look at some of the unique applications which make DAD such an exciting technology or attractive technology. So, the powder feed based AM can be used for the manufacturing of large scale components, which is not really realizable or easy to realize by other means, such as powder bed based techniques. For example, the Lens 850R system by Optomic has a work envelope of nearly 1 meter by 1.5 meter by 1 meter, or which is enough to build even some rocket components, say. Like I know of a company called Relativity Space, which is actually 3D printing entire rockets or at least entire components of rockets and actually using them for actual space travel. And such machines can be used to build or repair large volume components such as bliss. Bliss is nothing but a bladed disc, impellers, or shafts. Now, this can also be used to actually add features on any pre-existing part. And other uses such as cladding or feature addition on internal surfaces, such as here. So this is actually the internal surface of a cylindrical, say, component, and it cannot be easily reached or material cannot be new features cannot be deposited in such a region by other AM based processes. However, DAD based AM is actually capable. of depositing new features even in such inaccessible or difficult to reach locations. This can be accomplished by appropriate design of the cladding head. So in the example to the left here, we see a very long and slim nozzle which can actually reach difficult to reach positions or can actually go very deep into a component with some hollow section. On the right here, we see that there is a tilt of 90 degrees in the powder delivery channel. So the powder would initially get delivered along this coaxial axis, and here it is getting turned by 90 degrees and being deposited on the feature. Similarly for the laser, so there would be some mirror over here, which is actually rotating, reflecting the laser in that direction. And thus, on the right, we see that one of the features has already been deposited. So maybe the same feature is being deposited on the other side as well. These very challenging and strategic applications can only be covered by DED-based AM processors. Again, it can be used to actually make the functionally graded materials, which are objects whose properties are designed in a way to vary different part of the product. So the material property itself or the part property itself will vary as a function of the location. And this can be very useful in situations which are very demanding, such as extreme temperature service conditions. Say you have the tip of an aircraft, which is subjected to the most amount of drag and friction and heats up. So on the tip itself, we can have a coating of some ceramic-like material, which can give good high temperature performance and good hot hardness instead of making the entire part out of ceramic material. So along that direction, we will have a functional gradation where I have ceramic on the outer surface and metal on the interior. Another example is this human bone, which is very hard on the outside, spongy on the inside, and even hollow at the core, which is filled with the bone marrow. Similarly, the example of this coconut here, where as we go radially inward inside the coconut, the density as well as the hardness changes. First, we have a very coarse or very hard outer shell, this rough outer shell. Then we have this inner shell over here. Then the flesh of the coconut, and inside we have the water. And any of the properties may be changed for it to qualify as an FGM, such as the density, the chemical composition of the material, the color, even the magnetic properties may be changed. And this may be achieved in terms of a stepwise gradient. Say I have a very well defined, say this is my property or my characteristic, and this is my length scale, or say distance from any reference point or reference axis. And I can define the way in which this property should vary. So it can have some periodic step-like function where at a certain distance I achieve a certain amount of this property, or it can simply be continuous, need not even be linear. It can also be some non-linear behavior, but it is continuous and there are no discrete steps. Here, over one step, the property would be constant, say in this region or in this region. And in terms of visualizing the actual material itself, say I'm depositing some, say in terms of the density. So maybe the density will be fixed over this region, then over here, over this entire region, even though the density between the adjacent regions is different, it is constant over a certain length scale. And I have these sharp boundaries which are actually dividing these different regions. Again, it can be guessed that it is actually these boundaries which later act as the site at which the defects are mostly seen. Say if you are making an FGM of different materials, it is at the multi-material interface where because of say an incompatibility in terms of the thermomechanical properties or in terms of the expansion coefficients or simply the material chemistry itself because of the formation of some deleterious secondary phases or intermetallic phases, most of the cracks or other defects will be observed. Again, FGMs are mostly encountered in the building direction or in the Z direction, and rarely encountered in the build plane itself or in the XY direction. This is because for one plane, it is much more easier to keep the entire material composition constant rather than changing it in the plane itself. Another challenge of making FGMs is illustrated here. Say I'm using multiple nozzles to actually deliver the different powders. And ideally, the configuration of these nozzles is fixed around the laser source. They do not really rotate. So here to the right, I have the supply of tool steel powder, and thus it is expected that this right region will be rich in tool steel, whereas to the left here, I have the supply of copper powder, and I can expect that in a melt pool, this right region will be actually rich in copper. And in the absence of any mixing mechanism, say Marangoni convection or natural convection or buoyancy driven flow, the powders will not really mix homogeneously and will remain separate. Thus, when the bead is solidified, again it will be show this gradient, and where one side of the bead will be rich in tool steel, the other will be rich in copper. We can actually artificially augment this flow behavior by, say, using some additional means. One can be by using an ultrasonic vibration and using some horn sort of apparatus. The ultrasonic vibration can be transmitted into the melt pool, and because of that additional ultrasonic energy, the mixing can be enhanced and augmented, leading to more uniform chemical constitution. Of course, one of the oldest and most popular applications of these powder-based DED systems is the laser cladding and surface alloying, where we want to deposit a predefined layer of harder or stronger material or in any other way strategic material on top of an existing component. Thus, the component remains the same, and in terms of the cost and ease of production, everything remains the same. I do not even have to make a new component. I just strengthen it by adding some additional material, which is strategically important on just the top layer. And it attempts to modify the properties. So this is the surface properties only. Using similar or dissimilar material, either may be used by creating a new surface with desirable properties. And mostly it has been used to actually augment either the hardness or the wear resistance of the components. Here we see that even the laser cladded layer can have some gradation. So we start with an SS304 substrate, then we have a cladded zone of SS316L, and finally on top we have an alloyed layer of tungsten carbide, which is uh, a ceramic material, so suitable for high temperature applications. DD can also be used for part restoration. So say you have a critical part and belonging to, say, an aerospace application or an automotive application, and it fails in service. Usually what we would do is simply throw away the part and procure a new one, which is very costly as well as time consuming because of the high degree of customization in each of these parts. So one of the very important and upcoming applications is actually this part restoration, where I bring in a damaged part, I scan it using some 3D scanning apparatus to determine which is the damaged region, isolate that, and use that as my build region or my build volume. I generate a toolpath for depositing material in that small region only. And once we are done, it's like we have the original part restored to us. Of course, there will be certain considerations, such as the bonding between this newly deposited layer and the existing part, how good that is, as well as it will have to be finished properly to ensure continuity and smoothness. But it is definitely an application worth looking into. So for repairing purpose, the component is first digitized and transformed into a mesh representation. And this actually provides the CAD input, which can later be analyzed for extracting the repair volume and the toolpath planning. And this ability to repair will increase the service life, will reduce the cost of operation, as well as it will promote the design freedoms. So one of such applications has been showcased here by Wilson et al. In a 2014 paper. Other application is the grid stiffened structures, where we deposit some of these grids on existing structures to further stiffen them or to add some additional layers between them. They will have a high load carrying capacity as a result of this process, and these structures can be used to prevent some local flutter or vibrations, as well as they will have high bending stiffness and a very high strength to weight ratio. So in summary, the powder feed based DED or AM process has certain advantages and disadvantages. One of them is of course the high deposition rate. So not as high as say warm based processes, but definitely higher than say the powder bed based processes. It has the ready possibility of realizing the material based FGMs, as we saw. It can be used for the very strategic application of part restoration and has been in use for laser cladding since the 1980s. And we can also incorporate some in situ processes such as in situ rolling, in situ hammering, or a face milling operation after every deposition step, some laser shot pinning or ball pinning to depending on the end application that is needed. However, it has certain disadvantages also, such as no support mechanism can be made, and this is because here we typically use the same material for building the support and the actual build geometry. Thus, separating them later would be a really tedious task. The way to overcome is to use the high degree of freedom table or the high degree of freedom manipulator robot to simply override the need for any support structures and deposit the overhanging features directly. The layer thickness is of course very high, so not as fine as say a wet photopolymerization based process, which will lead to bad surface finish, and the resolution would be low, so tiny objects or tiny features are simply out of the question. Again, because of the way in which the powder feedstock is delivered to existing machines, the catchment efficiency is pretty low, the powder stream diverges, and the powder particles impinge the melt pool at very high velocities. So this is a showcase of the powder-based AM processes. So I have some additional content which I have prepared, uh, actually borrowed from Professor Durga's slides here at IIT Bombay, which showcase the various means of the powder production. Here for the this course, we simply assumed that the powder feedstock was available to us, and we used it in different deposition strategies using different technologies. But maybe it is also worthwhile to actually look into how this powder feedstock is made and what differences that processing methodology or the manufacturing method can actually bring into the final built part. So maybe I'm not able to select the links. Never mind. So the first is the case of water atomization, and I have a schematic here. This is um, by from a textbook by Dr. C.P. Paul and A.M. Gino. So a very good and concise textbook for additive manufacturing principles and technologies. So there are three types of atomization technologies available to us for generating the powder feedstock. They are water atomization, gas atomization, and plasma atomization. We'll look at each of them. So for water atomization, we use a high pressure water jet. And what happens is we have some liquid metal. So usually we'll have some metal feedstock, say in the term form of wires or plates, which are actually melted by some inductive or resistive heating to generate this vat of liquid metal. The liquid metal is sent into a chamber via a small orifice or the outlet nozzle, and then these high pressure water inlet nozzles spray that incoming melt the spray of liquid with this water, and this leads to the breaking of the molten stream into very fine particles and droplets. When these droplets solidify later, so usually this chamber length would be significant to allow enough time for the molten droplets to solidify into fine particles. Uh, they will get collected at the bottom. However, during this process, the oxygen pickup from the air would be pretty high. And so one way is to actually perform this, say, in an inert gas chamber, which will reduce the oxygen pickup. The powder feedstock size that we can actually obtain from this process would be in the say 30 to 1000 micrometer size, and it will have some 500 parts per million to 1% oxygen, which is pretty significant. And if we use some ultra high pressure water jets, then the powder size can be reduced further. However, the powder shape is still pretty irregular and it is not really spherical, so it will have some elongated or oblong type of shape rather than the clearly spherical particles. And because of the irregular shape, the powder flowability, as well as the final bead geometry, and even the gas pickup by the powder particle will be affected. The next technology is gas atomization. So here what we are actually looking at is this is a titanium cylinder or even called a titanium electrode, and it is constantly being rotated as it is fed into this induction coil. So because of this constant rotation as well as this feeding motion downwards, the titanium rod is getting heated and molten. That molten metal is getting poured into the chamber, and so here we have the molten metal, and it is getting so going to the next stage via some orifice on a nozzle, as shown here. And then previously we were spraying it with high pressure water. In this case, we spray it with some high pressure gases. This gas actually breaks the molten metal stream to form droplets again, and these droplets will then solidify into some fine spherical powders. Here, for the gas spray, usually the air or inert gas is used, or we can have a two-stage setup where we have a vacuum inert gas. So melting and pouring will happen in vacuum, and finally it will be sprayed with some inert gas. The oxygen content again is some 1000 parts per million to 1% if air is used, 100 to 500 parts per million if some inert gas like argon is used, or if this entire or if the melting and pouring stage is performed in vacuum, then the gas pickup, oxygen pickup would be significantly less at 50 to 200 parts per million only. In this case, the powder particles would be more spherical than for the case of water atomization. However, they are susceptible to forming porosities inside the powder particle itself. So earlier we were seeing porosities because of the lack of fusion or because of partial melting of the powder particles and other effects. However, what if your powder feedstock itself has some porosity inside? Thus, unless we melt it totally, we can never get rid of the inherent porosity. The third technology is actually plasma atomization, where we use the plasma, so high temperature and high velocity plasma to actually atomize the feedstock directly into very fine powders. So electric charge discharge in gas will produce a plasma arc, and this plasma arc ionizes the gas and achieves temperatures up to some 11,000 Kelvin. The leftover gas, which has not been turned into plasma, will get heated by this ionized argon gas and can also reach temperatures of some 2000 to 10,000 kelvins. The kinetic energy of the pressurized gas then breaks the molten stream into droplets, and the heat from the plasma liquefies it. The droplets again solidify into fine spherical powders as they travel down the chamber. This technology produces the finest and most regularly shaped powder feedstock, and it is also the smallest size. And thus, for very precise applications, it is actually recommended to use plasma atomized powder feedstock only. Here we also have a comparison of the powder characteristics as obtained by various powder manufacturing processes. So we see that for water atomization, gas atomization, the particle size is nearly the same. For plasma atomization, we can achieve smaller particles. Again, we see that it is always in a range because what we have is a distribution. There is no powder of a single size. It will always be distributed. The powder water atomization has high production rate. The particle sizes are however large, and the capital cost is low. However, it will have irregular particle shape as we discussed. Some satellites or some additional elements will be present on the powder which are not really desirable, and the particle size distribution will be very wide. So our distribution would, rather than being steep and being located in a narrow region, say this distribution can be pretty widespread. For gas atomization, it is very suitable for reactive alloys or alloys that can react with water. It can give you again a large particle size range and relatively spherical particles as compared to water atomization. However, again, satellites are present. There is some wide particle size distribution, and as we saw, the powder particles can also be porous. For plasma atomization, we use a wire or a powder feedstock. Why wire feedstock? Because we can then very precisely control the volume flow rate or material flow rate into my melting chamber, thereby controlling the generation rate of the powders. Thus, I can have some optimum amount of gas flowing in to melt and atomize the powders, and that will help me maintain the homogeneity of the powder batch. The powder particles which are generated from this process are very highly spherical, and also the powder size distribution is narrow. However, such facility is very costly to implement as well as to maintain and operate. And here we have some micrographs which actually showcase the difference in morphology of these powders. So to the left, we have gas atomized powders, which are relatively spherical when we look at the ones on the right, which are actually water atomized. So we see that there are hardly any particles which are spherical in shape. However, compare this to the plasma atomized powders and look how regular they are in terms of both the sphericity as well as the particle size distribution. And this slide showcases the size distribution as we were discussing. So even for the same range of distribution, the gas atomized particles will have a larger mean diameter compared to the plasma atomized particles. So this is it. Uh, Let us take a short break and resume later with our problem solving session. So we will resume around 8:28 or 8:30. So let us resume our session. So the first question is asking, in a powder feed based AM process, an off-axis nozzle is used to feed material into the molten pool. The material is then changed from A to B in the same setup with the same process parameters is used. The melting point of material A and material B is same, but the thermal conductivity of material B is 4 times higher than of material A. In such a case, find out the ratio of the catchment efficiencies for both the materials. So under the assumption that the powder is being fed from an off-axis nozzle, we can use the derived expressions. Notably, the catchment efficiency was proportional to the square of the laser power times cos theta by dp square k square into Tm minus T naught square. Now here we are seeing that some of the parameters remain constant. Setup is the same and the process parameters are the same, so the laser power will remain constant. The angle theta and thus its cosine will remain constant because I'm using the same setup. Only the even the melting point is same, but the thermal conductivity is different. So even this parameter, which actually is the difference between the melting point and the ambient temperature, even this remains the same. Only our uh, thermal conductivity is changing. Thus, if I were to just express it in terms of that one parameter, so this catchment efficiency would simply be proportional to the inverse of the thermal conductivity squared. Now, I have to find the ratio of the catchment efficiencies, which even simplifies our task further. So say I have to find eta b by eta a, and I already know that. So they are related to the square of the inverse. So this can be Ka by Kb whole square. And further it is given to me that the thermal conductivity of material B is 4 times higher than material A. So Kb is 4 times Ka. So this is or 1 by 16. And I'm asked to find the ratio of catchment efficiencies for both the materials. So eta B by eta A is 1 is to 16 or eta A by eta B is 16. Let us look at some of the options. And yes, so 16 is the correct option. So by simple manipulation of the obtained expressions and looking only at the parameters which are changing, we can obtain some qualitative relationships such as the one obtained here. In the second question, for a powder feed based AM process with an off axis nozzle feeding material into the melt pool, if the laser power is decreased to half the original power, what will be the corresponding change in catchment efficiency? So again, we have similar assumptions and a similar expression as we used last time. So let us rewrite it again. Eta is proportional to P naught square cosine of theta and dp square k square tm minus t naught square. In this case, the parameter which is changing is actually the power, and so expressing it in terms of just the power, I can say that the catchment efficiency is proportional to the square of the power. So the power of the laser is decreased to half. So say I have case 1 and case 2, then the laser power used in case 2 is simply half used in case 1. So eta 2 by eta 1 would actually be equal to P2 by P1 squared because it is directly proportional to the square of the power. It is actually equal to, say, in terms of P1, in terms of P2. So I have P2 and P1 is equal to 2P2 squared. So 1 by 4. Because catchment efficiency in the second case will only be 1/4 time catchment efficiency in the first. Let us look at the options. The efficiency decreases to 0.25 times the original, and this is the right answer. So these questions are very similar to ones that you'll encounter in your assignment, and I'm pretty sure that you would not have any difficulty in solving them. Still, for the sake of completeness, let us look into a few more. So again, in a powder feed based AM system with an off-axis nozzle, if the diameter of the nozzle is given as 8 mm and the injection angle is also given as 45 degrees, let us find out the projected area of powder on the horizontal plane. So just some prelude, as we already discussed. So when the beam is falling normally on the substrate, at the focus, its cross section would be circular. Say whether it is a converging beam or a parallel beam, the cross section would be circular. But for the case where the beam or the powder material is coming at an angle, the cross section remains circular no longer and instead changes into an ellipse. However, even for this ellipse, the minor axis still is equal to the diameter of the original powder beam or the powder channel. However, the major axis changes, and we are asked to calculate the projected area. So again, even for this scenario, an equation has been derived and illustrated in the slides. So I would be using it here, and the projected area is simply pi by 4 uh, d square by cos theta. Here we have d equals 8 mm and the ejection angle theta is 45 degrees. So let us plug in these values. If I do not interconvert, my projected area will remain in mm square and by cos pi by 4, and I'll just compute this. So this comes out to be 71.086 mm square. Let us look at the options. So yeah, that is approximately equal to 71 mm square. So option B is the right option. For the next question, it deals with the global energy density, and we are asked that if the power of the laser is decreased to half the original power, while increasing the scanning speed to double the original speed, how will the corresponding global energy density change? So we have two scenarios. Power of the laser is decreased to half the original power. So P2 is equal to half P1 and the scanning speed is increased to double the original scanning speed. Vs2 is equal to double Vs1. What will be a change in the global energy density? So we know that the expression for global energy density is equal to P by Vs times dl, which is the spot size of the or the diameter of the laser. So qualitatively, I can express it that the global energy density is proportional to P by Vs. And if we were to find the ratio of these global energy densities, so say GED2 by GED1 would be equal to the ratio of P2 by Vs2 by P1 by Vs1, or P2 by Vs2 times P1 this times Vs1. So P2 by P1 is half, and Vs1 by Vs2 is half again. So 1/4. Therefore, the global energy density in the second case will only be 1/4 of the global energy density in the first case. It can be said that the GED actually decreases to 0.25 times the original. But we can also intuitively think of it from a logical perspective that I am scanning a bead. Say this is my build plane. I'm scanning this bead on top of it. And what I'm doing is first I've already decreased the power, and then I have also increased the scanning speed. So already the power is less, and at the same point, the dwell time of the laser has also been decreased. So overall, each material point along this bead has less energy available to it because of the decreased power itself, which is incident, and second, the increased scanning speed, which leads to lower interaction times of the material with the laser or the energy source. Thus, qualitatively itself, I can say that the GAD will definitely decrease, and the extent of the decrease I can calculate from the derived expressions. Which AM process is more suitable for repair of damaged components such as shafts and turbine blades? So this might be easy because in some of the later slides we already saw how one of the major applications of DED based AM is repair. So we know that C is the answer. But let us actually try and think what disqualifies the other methods from such applications. So say in the case of powder bed fusion, we can clearly say that the build volumes are far smaller. Thus, a shaft cannot be accommodated into the build volume of a powder bed machine. Again, it will require a lot of say additional powder, which will be wasted or unless reused. But primarily, we can say that the smaller build volume is preventing it. Secondly, the sheet lamination. Sheet lamination is not really suitable for any repair based or any post processing or a feature addition type of operation because it can only use the sheets as the feed, so it cannot work on any existing part, as well as both the form and bond and form methodologies will be incompatible with any pre-built or pre-existing part. So even though sheet lamination can work with multiple types of metallic material irrespective of their metallurgical compatibility, can also be used to embed some fiber optics or some sensors into the material. And it is also a low hazard and low temperature process. Still, it is not suitable for the repair application. Now, when it comes to binder jetting, again, it will have a powder bed-like setup where the powder is already placed by a recoater. A thin layer of powder is already deposited on the pre-built layer, and I'm simply depositing selectively the drops of binder in selective locations to actually realize my part. However, it will also require a post process which is sintering. for actual generation of the component. The one we will obtain at the end of this binder jetting cycle is simply the green part. It is not really sintered and does not have the corresponding strength. And thus, we would not really want to subject our existing part to any additional sintering cycles, as it might change its characteristics. Thus, DED is the most suitable. So, during our slides, we have discussed extensively about the functionally graded materials. So, let us also give them some consideration. Additive manufacturing allows the manufacturing of functionally graded materials or FGMs. Some factors related to the process are listed below. The formation of secondary phases and intermetallics, the dilution, that is a deviation of actual chemical composition from the design composition, the thermal property mismatch, that is the mismatch of the coefficient of thermal expansion, and residual stresses. So, which of these above factors should be considered while choosing material combinations for FGMs? So, clearly, here we are talking about FGMs based on the chemical composition of the material. So, I am working with at least two materials, A and B, which I will combine by some means. I can have a continuous gradation. Say I'm building a part which is 100% A and 0% B at the bottom, and 100% B and 0% A at the top. In between, it can have maybe a linear gradient like 40A, 60B, 50A, 50B, and so on and so forth. Or I can also have uh, so maybe some layers will have a fixed composition and so on. Or I can also have continuous gradation where these material boundaries will not be visible to me and simply transition from one material to the other. Or I can maybe deposit them alternatively. So I can have one layer of material A, the next layer of material B, and so on and so forth to obtain a multi-material structure. This can also be called an FGM based on direct joining. I'm not really using any interlayer or any gradient. When another type of FGM is one which uses an interlayer material. So say I know that A and B are not metallurgically compatible, but there is a material C which is compatible with both. I can actually use it as an interlayer between these two. However, in any of these configurations, what I must look out for is some of the considerations between the choice of these two materials. So let us find out which of these apply. The formation of secondary phases and intermetallics. So if my materials A and B are not chemically compatible or metallurgically compatible, when I combine them, they may not mix well, or they may also lead to the formation of certain deleterious phases, which are the secondary phases, as well as some very brittle intermetallics, which will actually promote crack propagation and lower down the mechanical and metallurgical properties. So this should definitely be taken into account, whether mixing or combining these two materials leads to the formation of any intermetallics. This can be assessed from some CalFAT based or phase diagram based calculations, where I choose my input materials, I choose the temperature range, and I say across this range for this combination of materials and the concentrations, what types of intermetallic particles are expected. The dilution or deviation of actual chemical composition from the design composition. So say for such an example where I have these steps of 100%, 80, 60, 40, 20, and 0% A, if because of dilution, somewhere this from here, say in the 40% layer, I have a keyhole which is delivering some additional quantity of A to this layer. And here now this concentration is changed to 65%. Then my design gradient is affected and it is no longer the same. So my end goal may not be fulfilled. Thus, I have to take care of the deviation which can happen in terms of the change in the chemical composition. The thermal property mismatch. So say between material A and B, one has a very high coefficient of thermal expansion. So if you give it some amount of subjected to a temperature difference or supply some amount of heat, it will expand. Whereas you have some other material such as Invar, which is actually a nickel-based alloy, which has the coefficient of thermal expansion almost close to zero. So maybe some order of 10 power minus 6 or something, almost close to zero. So at your metallurgical boundary or the diffusion boundary, you are subjecting this entire system to some external temperature. Because of this temperature, say the top material will try to expand, whereas the bottom material simply shows no stimulus. In this case, this metallurgical bond might break. And thus, because of the thermal property mismatch, some cracks might get introduced at the interface. Similarly, the residual stresses. So if the type of stress or the amount of stress which is present inherently in either of these materials are different, again, the overall nature of stress or the state of stress at the metallurgical bond might be unfavorable and might lead to delamination and cracking. Thus, all of these above factors must be taken into account while choosing the materials for generating an FGM part. For powder-based AM processes, which technique of powder processing produces the finest quality powders in terms of both morphology and quality? Water atomization, we saw that the powders were not really spherical. They had somewhat of an elongated and irregular shape, in some cases oblong as well. And also they were far coarser. For gas atomization, while the particles were relatively spherical, their sizes were still large and they might also be susceptible to some porosity inside them. Whereas for plasma atomization, we saw that not only were the powders almost perfectly spherical, the distribution was also very narrow, and so they were relatively of similar sizes, and the overall powder quality was the same and finest among the three processes. Having proper sphericity and powder quality is important to ensure good flowability as well as good surface finish. Of course, we also need a distribution of powder particles to ensure good packing. If all of them are of the same size, the packing density will be quite poor. We need some to be smaller. However, we also want our distribution to be reasonably narrow and not too wide. Thus, plasma atomization produces the best quality of powders. Question 8 is asking, a functionally graded material can have variation in which of the following properties? In density, in chemical composition, in color, or all of the above. So just in one of the previous questions, we checked out how a change in chemical composition can make an FGM. In terms of density, as we already saw in the slides, the human bone or any mammal bone is a very good example, which is very hard and dense on the outside, spongy and hollow spongy on the inside, and often totally hollow at the very core. So density can also lead to FGM, or change in density can also produce FGMs. Color. In one of the previous sessions, we have looked at some examples of color-based FGMs, where the color of the manufactured part is changing along with location. And thus, changes in all of the above parameters can produce functionally graded materials. So that is all the content I intended to cover for today. So I will be happy to take questions if there are any related to this week's content. So if not, I thank you for joining in, and I look forward to seeing you again next week. This is Sourav Goswami from IIT Bombay. Thank you for tuning in.
Thank you, sir.